So now we're doing this thing called a continuity equation. So this is note number 10. Now continuity equation is just a summation of everything that's going in minus the summation of everything that's coming out. Essentially, I think it's very obvious that anything that goes in, so the net mass transfer to or from the CV during the time interval t. Wait, hold on, let me reorder my stuff. So I will bring out the laser and I will take away the sticky notes. Yep. So essentially, the net mass transfer to and from a CV during a time interval t is equals to net change, increase or decrease in total mass within the control volume during t. I think the way that I think of it is like drinking water. So say if we drink more water as compared to maybe expelling the water via you like taking a piss or sweating. Yeah, so input minus output, drinking water minus peeing out the water, that would be the net change in the mass within the control volume. Yeah, so say you drink like 5 cups of water, but while you are drinking 5 cups of water, you're also peeing out like 2 cups of water. So then the net change is actually only 3 cups of water that's like slowly building up in your body. Yeah, I hope that makes sense. Okay, so this is just a basic one. So you're at summation of mass minus the summation of mass that's coming out equals to change in the mass within the control volume. This is the actual formula that we are more interested in. Summation of the input, the summation of the mass flow rate via input minus the summation of the mass flow rate via output gives me the rate of change of the mass within the control volume. You can see over here, summation input, summation output, and the total mass flow rate into and out of the control volume representing, and the mass of the control volume over dt, which is the net flow rate. Is it the net flow rate? Let me take a look. Yeah, the mass flow rate within the control volume is the change of mass within the control volume. Okay, let's write down this formula over here so that we can keep track of it and use it in our future questions to solve. dm cv over dt. Okay. And this thing is called the continuity equation. Okay. Okay. Allow me to also write down what exactly let me write down what exactly the summation of the mass flow rate input and summation of mass flow rate output. So summation of mass flow rate input minus the summation of wait, input mass flow rate would be nicer to say, of input mass flow rate minus the summation of output mass flow rate. And this would be equals to rate of change of mass in control volume. Okay, let me read this out so I can keep that in mind. Summation of input mass flow rate minus the summation output mass flow rate is equals to the rate of change of mass in a control volume. Okay, now on this slide over here, it's talking about summation of the input mass flow rate is larger than the summation of the output mass flow rate. Essentially, you're drinking water at a faster rate as compared to you pissing out the water. This leads to a build-up in the mass that is in your body. As you can see, there's an increase of the mass of the fluid within the control volume with respect to time. Or you can say that it is called accumulation. This is just the reverse. You're pissing out more water as compared to drinking it. Output is larger than input. This leads to a depletion in the water within your body. You can see here, it's downward arrow. It's the mass of fluid within the control volume decreases with respect to time, depletion. This is when you're drinking water and you're pissing out water at an equal rate. So maybe you drink 2 liters of water every minute and you're pissing out 2 liters of water every minute as well. So there's no accumulation, neither there is depletion. The rate of change of the mass within the control volume is 0. There is no change. We are at constant. They call it steady state conditions. I'm not going to write this down because this is pretty obvious. So let us move on. Now, here they ask us to recall that mass flow rate is m dot rho AV. Mass flow rate comes from this equation over here, m dot rho AV. I've written this in under pointer number 9. When flow velocity v is normal to the horizontal cross-section area A, always remember that A must be normal to the velocity for this to occur. So let me just draw out an image here for better visualization. Mass flow rate input. M dot input is equals to the area here and the velocity that is coming in, and of course you need the density of rho. This comes from the fact that the mass of the water within this control system is equals to the area times the volume. If I call this dx, okay, it will just be area times velocity times area. No, it's not. Mass is not area times volume. My apologies. It should be density times volume, because density rho equals to mass over volume. Okay, rho equals to mass mv. Okay, so here, let me get rid of this a here and change this to density. Volume, that would be area times distance. Now distance dx is not one of our variables. Dx would just be area times velocity dt, because dx equals to v dt, where dx is the distance, v is the speed, and t is the time. Oh, e disappeared. Okay, so speed times times gives you distance. Speed times times gives you distance. Let me erase this, because this is just some working. Now, I want to note right here that this is actually a unit mass. So this dx is actually infinitesimally small, and it is so tiny that it can be just a distance over here. The part is this length. There is a mass of dm over here over, well, it takes up a pipe's distance of dx. So now we want to change. Oh, what happened? Right here. I bring this tm down. We want to show this in m dot. This would be dm over dt. We bring the t over to the denominator. We are left with rho av. Hence, we have got this formula right here. This derivation is shown in 9 as well, over here. Now, this v must be normal, or in other words, parallel. Sorry, apologies, perpendicular. Normal means perpendicular. Allow me to draw a tiny perpendicular sign over here in the subscript, perpendicular to area. Take a look at this. Hence, in 4.41 becomes this formula over here, where we plug in our rho av into the formula up here. M dot replaced with rho av, summation sigma m dot, summation sigma rho av, minus summation output m dot, minus summation output rho av, equals to dmcv dt. Allow me to write down this formula, and I'll just write it in 10 as well, since it is something similar. Blue pen. Summation input rho av minus summation output rho av is equals to dmcv dt. Okay. Now where the fluid stream enters and leaves the control volume, normal. So yep, this is normal. Let me introduce the normal or the perpendicular sign over here for V. Perpendicular sign. V is perpendicular to normal surface, which I just said. Okay, Now, in general, velocity may not be normal to the surface. It usually doesn't happen. It usually comes out at a weird angle like over here. Resolve velocity forces v in a vector into components normal vn and tangential vt. So we resolve this one over here to normal and tangential. The control surfaces, we use trigonometry to get this. Only Vn is responsible for bringing or transporting the fluid out of the CV. Vn, it shoots outwards. For Vt, you just slide along the control volume and it will not escape the control surface. No, you slide along the control surface. I think I said slide around the control volume just now. Okay. Elemental mass flow rate out of the CV would be m dot rho avn then equals to density rho av cosine theta. So I will not write all these junk over here. I'll just make a simple note. Resolve V into V normal via trigonometry. I'm lazy, so I'll just write trigo. Via trigonometry to ensure parallel to control surface. Okay, I think we're done with this concept over here. There's this little red color thing up here. Let's read it. It is the component of the velocity normal to the control surface which brings the fluid into or out of the control volume. Yep, so again, we are talking about normal over here. There's this little vector, unit vector over here that shows you that. In general, 4.4.1 can also be written, yes, so it's just essentially the exact same thing. I just drop in a little n at the outside here, little n over here, and yeah, because you're happy. Inflow streams, outflow streams. Right, I mean, there's a reason why there's a little n over here. You actually don't need to write this. I think this is just for visuals. Vn is the velocity component of the normal to the control surface. We just said about that just now. 4.4.1, 4.4.2, and 4.4.3 are known as the mass conservation equation or continuity equation. Mass conservation. Yes, we all have been doing continuity equations all along. So yeah, I mean, cool. Proper choice of control volume helps to simplify analysis. So yeah, you need to think through which is the control volume you want to talk about. We do not like our control volumes to be slanted. That's a little pointless because you still need to resolve forces, which is very tedious. Just make it vertical. I think lesson over here it says try to choose control surfaces normal to the flow equations to simplify calculations. It's a given. I'm pretty sure everyone will do that. Steady flow. What is happening over here? Steady flow does not change with respect to time. So is it true that steady flow it's always input is equals to output? I think so. I think this is a very important concept. Let me write that down. let me write that in black. If question says steady flow, blue, dmcv over dt is equals to 0. Summation of input rho AV equals to summation of output rho AV, where V is velocity. So the total mass conservation, total mass flow rate entering CV is equals to the total mass flow rate leaving CV. I mean, yeah, because it's steady. So, yeah. Let me think about whether there's unsteady flows, steady flows where this does not occur. Okay, I can't really think of it, so yeah, I think I'll just accept it. Let's work on this example. Let me grab out my example questions. This ME2134 untitled notebook. Put it aside. Okay. Example 1. Oh, I think the example, yeah, this okay, let me just write this 4.2.2 example 1. Pencil 4. Sorry about that. 4.4.2 example 1. Alright. Summation of the input, mass summation of all mass flow rates via input minus the summation of all mass flow rate via output is equals to M1, which is an input, M2, which is an input, goes in, it goes in. Now we're talking about output over here. Output comes up. Wait, we're trying to find the output. So negative M. Oh, why is it in pen now? Or pencil? Negative M3. They're saying this is a steady flow. So steady flow, the summation, the rate of change of the mass in the control volume is equals to 0. So dmcv over dt equals to 0. M1 plus M2 minus M3 is equals to 0. M3 is equals to M1 plus M2. We plug in the values, 2 plus 3, you will get 5 kg per second. As you can see, 5 kg per second, 5 kg per second. Our answer is correct. Now let us do this example 2 over here. Wait, hold up. Let me just check the questions at the back. Okay, let's do this example 2 over here. 4.4.2 example 2. Input steady flow, so dmcv over dt, the rate of change of mass within the control volume, is equals to 0. Rate of change of mass oh, the m I wrote too small, is equals to the sum of the mass flow rate via input minus the sum of the mass flow rate via output is equals to 0. Now let us try to find the sum of the mass flow rate via input. That would be here and here. So m dot 1 plus m dot 4 minus the output will be 2, 5 and 3. So m dot 2 minus m dot 3 minus m dot 5 is equals to 0. Alright, let us reorder this so that we do get rid of all the negative signs. M dot 4 equals to m dot 2 plus m3 plus m5, m dot 5. So there's really no m dots anywhere. So I guess we can just make use of these things over here, or the respective variables to find m dot, which is essentially just rho AV. So we plug that in, pencil, let me change the color. Why is it still ordered wrongly? Give me a moment. Red should not be over here. Red should be here. Green shouldn't be over here. Green should be here. Okay, so let me use orange. So it is rho 1 V1 rho AV. I would like to write it in the proper form. A1 V1 plus rho 1 A1 V. Oh, apologies. It should be 4 here. A4 V4 equals to rho 2 A2 V2 plus rho 3 A3 V3 plus rho 5 A5 V5. Okay. Yep, and you can see that we have something similar over here, which is good. Now let us take a look at this. A single stream, one inlet station, station 1 and 1 outlet station. What is this all about? Single stream. Oh, so there's only one single stream inwards and one single stream outwards. And it's a steady flow. Okay, I mean acceptable. That's it? We don't have any other concepts over here to teach. We don't care what's happening inside as we assume control volume. So control volume. So you don't know what's happening in here. It's the enclosed surface. All we need to care about is what's coming in and what's coming out, and we know we have a brief idea of like the mechanics within. Yeah, I don't know how else to explain it. Conservation of mass for steady incompressible flows. Steady incompressible flow d over dt is equals to 0. Density equals to a constant. Steady incompressible flows. So yeah, so wait, where is my notes for chapter 4? Chapter 4 notes. Let me pull this over here. Right. So if question stays steady incompressible flow, now I need to write smaller. Okay, if question says steady in and let me underline the word steady to show that there's actually a new concept over here. Still dmcv dt is equals to 0. Of course, dmcv over dt equals to 0 is just this is equals to 0. You can bring this over to get something similar over here. I shall not go through everything again. You can drop hold up, you can actually, okay, let me write down this. So sigma input rho AV equals to sigma output rho AV. This is actually a sigma, I think. I didn't write properly. I'm not gonna rewrite it. Wait, just a bit. Let me change this underline to another color. Perhaps red. Now, because it's steady, density is equals to density is equal. Density, let me write that down. Density equal for steady flows. Hence, we get it back to red color. Sigma input rho AV, no more rho. AV equals to sigma output AV, and hence I can call it even further sigma input Q equals to sigma. Oh man, that's one ugly sigma. Output Q. Okay, so now what's happening over here is the conservation of volume. Wait, just now, yeah. So this is the volume flow rate. Q is volume flow rate over here. You can take a look at over here, the Q, AV, change back to Q. This is volume. So if this is continuing equation, which is the conservation of mass, this is the conservation of volume. But here's something. Is it important? It's not, because it is only when it is steady and incompressible. Steady and incompressible. It lies under the fundamentals of the continuity equation, which is the conservation of mass. So yeah, it's more or less useless. This can be easily derived. Okay, wait. Allow me to add in continuity equation / conservation of mass. Alright, so yeah, I'm gonna do 4.2.2 in another video. See you.